Hello. Oops. Okay, so you guys are looking into my room there. Move this over a little bit. And let me go get the door. All right, we have 3 people here. Let me see, what time is it? 11:31. So we'll go ahead and get started. So just to review, this is what has been happening this week. And remember, all due dates that are in Google Classroom are for your pacing. The assignments for the week, as long as they're in by Saturday at midnight of that week that they're due, you get full credit for it. No point deduction for being late. And that doesn't mean that as soon as you submit it, I'm going to grade it. When it's due, I'll go ahead and grade it. And then things that are turned in after that point, I'll get to as soon as I can, probably on Saturdays most of the time. So what was due on Tuesday were the inquiry stations. That was a video. If you couldn't do the video, then a script. What was due Wednesday? Close reading. So the chart and the paragraph were due on Wednesday. The static cat CER, which should have been pretty quick because you had 4 different answers already given, and you were to explain which 1 or 2 you agree with. As I said, there was no one that was totally correct. There were flaws in all of them. But still, that should have been pretty quick for you to do. Then we have the PhET Sim. What is this showing here? We have the PhET Sim was due on Thursday, and the study guide, no, student choice CER on Friday. So you pick the one. There were 3 different ones to choose from, and you pick the one that you want to submit. And so that's what's due today. Is that due today? Yeah, that's due today. So that's by midnight today. And again, as long as you get it submitted by midnight on Saturday, so tomorrow, no point deduction for being late. So what are the things that I want to go over today? When I was reading your work, I saw a lot of talk about electric charge being created. And I know that one of the students in that static cat CER said that. That's wrong because of conservation of energy. I hope that you were able to get to the close reading, because it's pretty clear in that close reading that there's conservation of charge. Just like we had conservation of energy, that means the electric charge cannot be created nor destroyed. All right, so watch how you're describing what's happening with static charge. The electrons are moving. When you have conduction, when you have direct contact, sometimes it's friction, sometimes it's just touching. But when you have direct contact, the electrons are moving from one object to another. When you have polarization, they're moving from one side of the atom or the molecule to another. And then the same thing with induction. It's moving from one side of the object to another. I don't see any questions yet, so let's go ahead. I wanted to cover Coulomb's law today, but there are two assignments that teachers posted in the last 24 hours on Coulomb's law. I thought we were kind of covering that this week, but we'll get to one of those assignments next week. Um, and then I can post the other as extra credit if you like, or maybe I just won't even post it. But I wanted to talk about clean rooms. So, my experience with clean rooms when I was working at Lockheed Martin one summer. I think I've talked about this before that I've worked in industry 3 summers as a teacher in order to bring those experiences back to you. So here is a picture of our group going into, well, we've already gone through the clean room process. So that's this picture here. That means you have to put things on over top of your clothes, including your hair, including your shoes. And then you go into a room, they blow all the particles off of you, and then you go out of the room. So where am I? Here. I lost my finger now. You probably don't care anyway. Where am I? Where's my finger? I think that's me right there. That's me right there, and I'm sure you can't see much of anything. But with electronic devices, it's really important that there's no static charge happening anywhere in the room. So that's a little bit more stringent than this clean room here. That was, like I said, that was at Lockheed Martin. And in the back, you can see there's a bus there that they're constructing. And actually, there are electronics that are in that inside that bus, but we weren't able to get close to that bus. We had to stand behind the line to observe what was happening. So the bus, that's like the container for what they're sending up into space for a satellite. The electronics, of course, are very important in making sure that everything that's supposed to happen on that trip happens. Um, Sometimes they have an umbrella of solar panels that open up, and getting from the Earth to their orbit, all of that stuff is packed in and closed up. So the electronics tell it what to do when. So it's really important that the electronics work correctly. So you may have noticed this in your experience anyway, but electronic devices are very sensitive to static charge. So if you're holding something like a motherboard, it's important to hold it from the edges. You never want to come in direct contact with anything that's on that board. It's important that you are staying grounded. So that means grounding. When we talk about grounding with electronic devices, that means any extra charge that's on you is running off of you. So when you have a plug that has an electric plug that has the three prongs, that middle one, that's the one for the ground. So that's taking any extra charge that's on the device is being sent directly to that wire, and that's actually sent to the ground. Because, like when we talked about clouds, the ground is so huge, the clouds induce a charge on the ground, but the ground is so huge, it's really very easy to dissipate that charge. Um, so that wire in the electric socket is sent directly to the ground where that charge is dissipated, and it doesn't harm anyone that way. Um, So everything has to be grounded in that room. That means your hands have to be grounded. I'm looking for the picture I have of that. Your hands have to be grounded. And here we have, I have a picture of a person that's building. Is that a keyboard? Well, it's a circuit board. So she's working on the circuit board. And you see this that's on her wrist? That's taking any charge that might be on her hand and it's sending it through a wire to a ground. So that's constantly being drawn off of her hand. And then up here, we have the same thing on a boot that a person's sock. So sometimes this is going to your sock, and then the sock is grounded to a rubber casing on the outside of your shoe. So besides being in a clean room, they have to take these extra steps to be sure that they're not damaging what it is that they're working on. To me, that's pretty exciting. It might not be cool to you, but what can I say? Um, so when you're working on electronic devices, you need to have your work surface and the floor has to be the static has to be dissipated from there. So that means like the ground, it has to be drained off, it has to be discharged off. Um, you have to be sure that you don't have materials like styrofoam. Now, styrofoam is a brand name. I don't typically use the word styrofoam. I typically say foam. Um, Vinyl, plastic, and some fabrics. Have you ever noticed when you throw your clothes in the dryer, if you don't get that the bounce sheet in there, the dryer sheet in there, when you're pulling your clothes out, they're all crackling and they're stuck together. That's because of the static charge. So your fabrics, they have um, that likelihood to be building up static, especially when we have friction that's happening, like in the dryer. Um, Sensitive components like electronics, they have to be in shielded bags or boxes. So they can't be just left sitting out on the table. They have to be put into a shielded bag or box. Have you ever received electronics in the mail and they have this? It looks like foil, but it's really not, but it's in a special bag. So it's not a plastic bag, it's in a special bag. That's because it's being protected from any type of static charge. And again, circuit boards always have to be handled only by the edges. If you go ahead and touch anything on that circuit board, you've shorted it out, it's not going to be any good. And the smaller that our electronic devices get, cell phones used to be like about this big. They call them mobile phones. And we're being really good at getting those smaller and smaller. Hopefully, we'll be able to get into that when we talk about electromagnetism, but our time is somewhat limited. Um, can't do as much as we could as if we were in the classroom. Um, but nevertheless, circuit boards, you can only touch on the edges, and our electronic devices are getting smaller and smaller and smaller. So it's even more important now because one wire is so close to the next one. So it's very important that they stay separated. It's very important that there isn't a charge that it collects and then shorts out that a particular piece of it, and the pieces are so close that it's easier to happen than it used to be. The other thing I wanted to talk about today, let me see what kind of questions we have. What's the fastest way to contact you for the fastest response? Um, Typically, I check my email. Usually, I go through the Pittsburgh Unified email first, and then I go through the um, the ones that are showing up in my Gmail. Um, but I typically I don't answer my emails after 3:30 p.m. I have to do a cutoff because it's too consuming to be grading work, to be trying to answer emails all day long, and to be grading your work, and to be making assignments and doing that all day long. And then after 3:30, continuing with the emails. I can't do that. So I do a cutoff on answering emails at 3:30, sometimes 3 o'clock. Um, I can't access the slides with the questions and links. I don't know what slides I provided that have questions and links. So, Gail, if you can tell me specifically what slides it is that you're trying to open, maybe I can help you with that. Darren is saying open it with Docs, so you can copy it or download it, either copy it to your Docs or download it. Nick. Hi, Nick. How are you? Hi, everybody. It was so good to see some of you in your videos that you submitted this week. It just made my heart sing to be able to see you again. So I hope that everyone is still managing through this process that we're going through now. And then the other thing I wanted to talk about today was laser printers. You probably don't know that's all about static charge. That's how that happens. So I have a picture here of a laser printer. Let's see how close we can get that to you. So the first step is the data streams from your computer to the circuit board. So you have information that's being sent to the circuit board. This is inside your printer. All of this is inside your laser printer. From the circuit board, it goes to a high voltage corona wire. So I don't know if you can see the little like lightning bolt type thing that's happening there. That's the corona wire. So that's high voltage. And what that does, that sends a signal, depending on the signal that the circuit board received from your computer. It sends a signal to this drum here. This is a, what's it called? Photoreceptor drum. That signal makes the entire surface of that drum positively charged. From there, we get a laser signal. So now we're going back to the circuit board over here. So the circuit board is telling the laser, so it's relaying information to the laser. The laser is sending a signal to a mirror. This mirror bounces the signal to the drum. Now this mirror can move. Typically the laser doesn't move, but the mirror moves so that the signal that's being sent here corresponds with the information that the circuit board is telling the laser to do. Now, what that signal from the laser is doing, it's making wherever this laser is pointing to on the drum, it's making that spot negative. So the negative is where the ink should be. So that's the image that the information was sent to the circuit board. It's making anything that should be the ink that should be black, it's making that negative. So now the roller applies that negative to the toner. So here's a roller that has the toner in it, and the toner is positive. So that only sticks to that negative parts that are on the drum. And now we have the paper. Is this where the paper? No, paper's coming from here. paper comes up the ramp, the paper is negatively charged and it goes over the roller. That negative charge attracts the positive toner that was put onto the drum. So it attracts that toner onto the paper, but it's not sealed on there yet. It's just barely sitting on that paper. And from there, it goes to these two rollers that these are hot, and that glues the ink. It fuses the ink to the paper. And when you get it out of the printer, have you ever noticed that your paper is hot? Well, it's hot off the presses. And that's because of the static charge process that it goes through inside your printer. Then it finally has to be fused to the paper in this last step, and it's hot off the presses, literally hot off the presses. So that's pretty much all that I have for today. I could talk about Coulomb's law. That was also in your close reading. Coulomb's law says that the force between two charges, so we have two charged things, maybe it's the can and the wand. If you saw the video for the inquiry stations, you rub the wand with the fabric, and that gives the wand a charge. Then you bring it close to the soda can, and it induces a charge in the can. So the force that's acting between those two, there's a force that's pushing the can towards the oppositely charged wand. That can be calculated with Coulomb's law. And that is very similar to Newton's law of gravitation. So Newton's universal law of gravitation, we have F equals G times one mass times the other divided by the distance between them squared. And then Coulomb's law, so this is force due to gravity. And Coulomb's law is the electric force between two objects is K. Now we've used K before, so do not confuse this with the spring constant, times Q1 times Q2 divided by the distance between them squared. So do you see how similar this is? G is a universal gravitational constant, 6.67 times 10 to the minus 19 newtons meter squared per kilogram squared. And this is our Coulomb's constant, which is, do I have that written down? 9 times 10 to the 9th newtons meter squared per coulomb squared. So this is a constant. This is a constant. You have the mass of one object times the mass of the other. This is the charge. So this is measured in coulombs. So this is the charge on one object times the charge on the other. And they're both divided by the distance between them squared. Now, one thing that I do want you to notice is that G is 6.67 times 10 to the minus 19. Is that right? I want to be sure that's right. Oh, minus 11. I'm not going to put the units down for the moment. And K is 9 times 10 to the 9th. Is that right? Yes, and that's Newton's meter squared per coulomb squared. So the big thing that you have to be looking at, this means that you have 10 zeros before the 6 after the decimal point. So you have 0.0, you have 10 zeros, and then 667. This means after the 9, you have 9 zeros. There's a big difference between the magnitude. Remember, when we say magnitude, we're meaning size of this compared to this. Gravity is a weak force. I know that's something that contradicts everything that you know from your experiences. Gravity is an extremely tiny force when you compare it to the electric force. The electric force is what makes our world look like it does. It's what keeps this marker, when I set it down, when I set it down, that's what keeps the marker from falling to the center of the earth, is the electric charge that's acting between the atoms and molecules in the object. So solids, we know that the atoms and molecules are closer together. Liquid, they're close, but they're moving around. And gas, they're all over the place. So the reason that materials are held together is because of that electric charge that holds them together. It's incredibly strong. The nuclear force is a strong force. That's what holds things together. That's what makes our world look the way it does. That's what keeps us from falling through the floor, is the electric charge that's holding that floor together. So that's all that I want to say about Coulomb's law. We're not going to do any calculations with it, but just like Newton's universal law of gravitation, when you have things that are close, the force between them is greater. We don't really need an equation to tell us that, right? When things are further apart, let me get it within the screen. When things are further apart, the force between them is smaller. We know that. It means that the force is inversely proportional to the distance between them squared. It's inversely, that means the force is in the top of the equation and the distance between them and squared is in the bottom. And force is directly proportional to the charge, the product of the charges on the two objects. So that's all I have for today. I see a question. We have to use the chart. No, just write the paragraph. The chart is for you. The chart is for you to organize your thoughts. You do not have to fill in that chart. So I do want to mention that. One other thing, that read the instructions on the assignments. I know this is a whole new world for you. It's a whole new world for us too as teachers. So we're using the same type of strategies that we've used in the classroom, but we're not necessarily sticking to the same expectations, right? So be sure to read the instructions so that you're not doing work that you don't have to do. The forms are the same forms, so they may say, okay, fill out this form like this, but read the instructions so that on the assignments, so that you know what the expectations are. There were a few people that for the inquiry stations, they filled out the inquiry forms and didn't do a video or a script at all. So save yourself that trouble and read those instructions. When you click on the assignment, you click on the tab part where it has the name of the assignment, and then the instructions pop up as well as the attachments. G and K are always like that. Yes. So when we're using G, the universal gravitational constant, that's not the same as a small letter G. It's always this, and I didn't put the units down. I always put units down. I didn't. And then K is always this. Spring constant, the K for spring constant is different for every spring, right? Every spring is different, but gravity acts the same on all objects. And I believe when we did forces, well, I don't know, maybe I wasn't there for that. Yeah, when we did forces, we did the calculation showing that on Earth, this force between two bodies comes out to be 9.8. I'm sorry. The gravitational constant um, is the 6.67, but it gives us an acceleration, F equals ma, of 9.8 meters per second squared of objects on Earth. We can do this for different planets. So you use the 6.67, but planets have different mass and they have a different distance from the center of the planet to the surface. So you can calculate the gravitational acceleration due to gravity on each of the planets using this one. I don't see any other questions, so have a good weekend and don't forget to finish up today's assignment. Bye. Have a good weekend.